3D printed objects are rapidly becoming popular. An important question is how to minimize the cost of 3D printing by using less material to support or fill the objects, yet obtain a strong and durable model. In this paper, we introduce a new manufacturing paradigm of injecting the 3D shape with super strong materials. We use minimal surfaces to segment and hollow the volume interior. Triply periodic minimal surfaces define a multi-scale porous structure, which is smooth and fully connected. Injection paths for super solid materials. After the object is 3D printed, we inject liquid materials through the TPMS. The injected fluid smoothly propagates and fills the tunnels completely. Our TPMS tunnels correctly guide material distribution in the interior in order to sustain the required stress factors. Once solidified, these materials yield a super strong support of the shape. Initially, we perform structural analysis using finite element methods and obtain the stress field. We use the stress field to define an adaptive TPMS function in the object interior. The TPMS structure is non-uniform, with large frequencies in weak regions and vice versa. This allows the distribution of more material to support high-stress regions. Our optimization consists of two parameters. One is the TPMS frequency, which yields a globally adaptive tunnel structure. Second is the tunnel width, which allows a fine-grained control over the material distribution. Our optimization iterations stop when the resulting model can sustain the required stress factors. In the final step, we create an entry hole on the shape's least visible region for injecting the material inside the tunnel. Our super strong TPMS allows injection of a wide range of materials in a fast and easy process. 3D printing of super strong objects becomes highly efficient in terms of printing time and material, as the object's interior is hollowed by TPMS tunnels. Our method augments the traditional 3D printing process, as it now interacts with exterior materials.